Hi everyone, welcome back to my channel, The Space Koala. My name is Lutza, and today we're going to dive into the world of field of view, magnification, and resolution in astrophotography. These concepts can be a little tricky, but by the end of this video, we're going to have a clear understanding of how these all work together to help us capture these stunning images of the night sky. Let's get into it. Let's start with magnification. When people think of telescopes, they often ask, how much does it magnify? This is a very common question, but turns out when it comes to astroimaging, this is not quite the right one. In visual astronomy, magnification is straightforward. It's calculated by dividing the focal length of the telescope by the focal length of the eyepiece. For example, if your telescope has a focal length of 1,000 millimeters and your eyepiece has a focal length of 10 millimeters, you get 100 times magnification. However, in astrophotography, we typically don't use eyepieces. Instead, we tend to attach cameras directly to the back of the telescope in place of the eyepiece, and this is where the concept of magnification becomes a little bit more complex. When we talk about magnification in astrophotography, what we're really talking about is the field of view, which is determined by the focal length of the telescope and the size of the camera sensor. The longer the focal length, the narrower the field of view, meaning you'll have less of the sky in the picture. Conversely, a shorter focal length means a wider field of view, meaning you get a larger portion of the sky in your picture on the camera sensor. The field of view is essentially the portion of the sky that your camera is able to capture at once. It's directly dependent on two factors, the focal length of the telescope and the size of the camera sensor. Imagine we're looking at a section of the sky through the telescope. Our goal is to figure out the angle or field of view that our telescope can see. For example, let's say that our camera sensor is 36 millimeters wide, which is a full frame sensor. And let's say that our focal length is 250 millimeters, like this Red Kit telescope here. Using simple math, we can actually calculate the field of view without any further information. This is a diagram of this setup with the front lens and the sensor. Look at this triangle here. The base is the width of the sensor, in our case 36 millimeters. The height of the triangle is the focal length of the telescope, which is 250 millimeters. The angle at the top represents the cone of light that we're trying to find. First, we need to understand that our sensor captures light from both sides of the center. So we'll split the sensor width in half, which gives us 18 millimeters for each side. This also conveniently gives us two equal right triangles. And a right triangle means we can use trigonometry. A quick refresher. The tangent of alpha is the opposite side divided by the adjacent side. 18 millimeters divided by 250 millimeters. This gives us the formula tan alpha equals 18 over 250. When we divide 18 by 250, we get 0.072, so tan alpha is 0.072. Using a calculator, we find that alpha equals 0.072 radians or 4.12 degrees. Remember that this is only half of the field of view because we calculated the triangle on one side of the sensor. To get the full field of view, we need to multiply this by 2. So at the end, the full field of view is about 8.24 degrees. There you have it, as simple as that. Using some simple trigonometry, we calculated that the field of view of our telescope is 8.24 degrees with this sensor. This tells us how much of the sky we can capture in a single image. Now that we understand where this is coming from, we can actually simplify it by quite a bit. What we did was actually the following. We calculated half the field of view by using half the sensor. So we got tan of alpha over 2 equals half of the sensor size divided by the focal length. As long as the angle is reasonably small, which will always be the case for telescopes, we can use what is called a small angle approximation. What this means is the tangent of alpha is actually equal to alpha when expressed in radians. A radian is just another unit of measurement for angles. Simplifying with this gives us alpha over 2 equals half the sensor size divided by the focal length. Now we can multiply the whole thing by 2 and we just get alpha equals sensor size over focal length. As this is measured in radians, we just have to convert it back to degrees to make it more convenient, hence the 180 over pi, which is 57.3. Therefore, we can calculate the field of view of any telescope sensor combination just by dividing the sensor size by the focal length and multiplying it by this number. Obviously here we were working with the longer side of the sensor, but we can also calculate the same thing for the shorter sided sensor, and then we can get the whole field of view rectangle. Alternatively, we can work with the diagonal to just work with a single number. Now, understanding this relationship from this formula, we can see that to zoom in more, meaning a smaller field of view, we can either increase the focal length or decrease the sensor size. For example, if I put this planetary camera on the same telescope, it has a tiny sensor of 5.6 millimeters. I put it on the same telescope. I'll get 5.6 divided by 250 times 57.3 equals 1.28 degrees of field of view. Let's just compare what that looks like on the Andromeda galaxy. That is definitely much more zoomed in. By understanding this relationship, we can choose the right combination of equipment to capture the desired portion of the sky exactly. Planning your astrophotography sessions in advance, knowing what field of view you want to capture exactly, can greatly improve your chances of getting stunning images. Fortunately, there are numerous tools available that help you visualize the field of view of your telescope and camera setup before you even step outside, and without having to do any of these calculations yourself. Now, let's take a look at a couple of popular options: Sky Safari, Stellarium, and Telescopius. These tools all allow you to input your telescope and camera setup, and they will overlay your field of view rectangle on a map of the night sky, helping you plan for your imaging targets. This is my personal favorite, Sky Safari. You can enter your telescope's focal length and camera sensor size to see exactly what will fit within your frame. Stellarium offers a very similar functionality, allowing you to visualize your field of view against celestial objects in real time. Telescopius provides a web-based solution with customizable overlays and detailed planning tools for astrophotography sessions, even helping you to plan mosaics. These planning tools are absolutely invaluable for astrophotographers, helping us efficiently plan our imaging sessions and ensure that we actually capture the objects that we're interested in. By visualizing the field of view beforehand, we can optimize our setup and make the most of our time under the stars. Let's look at the examples we saw earlier, a full frame and a planetary camera sensor on my 250mm Red Cat telescope. It's calculating the same thing we saw before, and we can compare how a specific object would look with each of the setups. Of course, we don't have to change the sensor. We can also choose to use a much larger telescope. This is my picture of the North American Nebula. Let's just focus here on the lower left side, which the structure is called the Cygnus Wall. This was taken with the Red Cat. This here is the exact same structure, just taken with my Celestron C11 telescope with a focal length of almost 2,000 millimeters or 2 meters. Now we know why when somebody asks, so how many times is it magnified? There is no straightforward answer. Magnification in astroimaging is not a single number because it depends on a combination of focal length and sensor size. Unlike visual astronomy, where eyepieces determine magnification, in astrophotography we talk about field of view, as well as another measurement called image scale. Image scale, which is simply the amount of sky covered per pixel, is calculated simply by taking the area of sky covered divided by the total number of pixels. In the example before, we had an area of 8.24 degrees covered. On this sensor, the longer side consists of 6,072 pixels. This gives us an image scale of 8.24 divided by 6,072. We can convert 8.24 degrees to arc seconds by multiplying by 60 to get arc minutes, and then again to get arc seconds. This gives us 4.88 arc seconds per pixel. This is the image scale of this photo taken with this combination. It tells us how much of the sky is covered by each of the pixels of the photo, which is a much more relevant measure in astrophotography compared to just a simple number to express magnification. By the way, we can conveniently take our previous formula, and instead of applying it on the entire sensor, we apply it on a single pixel. Then we get alpha equals 57.3 times pixel size divided by the focal length. This, of course, gives us an extremely small number, as it is in degrees. Once again, multiplying it by 60 times 60, 3,600, we get it in arc seconds. We get the number 206,265. The pixel size of the camera is 5.93 microns, so 0.00593 millimeters. Plugging all these numbers in the formula, we get 4.89 arc seconds per pixel, which is close enough to the other method we calculated before. Again, this number is a really good descriptor of magnification because it tells us how much of the sky has been covered by a single pixel. In other words, telling us what angular level the sky has been magnified to. Based on all this, one might think, I would just get a small telescope with a small sensor with many tiny pixels, and I'll get a nice high-resolution image that way. Unfortunately, it's not that simple. Resolution in astrophotography depends on a number of factors: the aperture of the telescope, the focal length, and the pixel size. So far, we only mentioned the latter two, but it's the aperture of the telescope that will be the property limiting how much we can physically magnify. The larger the aperture, the more detail and the more light the telescope can gather. Let's compare two setups: a large telescope with a larger sensor and a smaller telescope with a smaller sensor and even smaller pixels may physically have the same exact field of view, but the larger telescope will be able to resolve much more finer details. We've seen previously that we can manipulate field of view by playing around with the sensor size as well as the focal length. So we can combine these two telescopes with sensors that will result in them having the same exact field of view. We can do this, but the details resolved by each of them will obviously not be the same. For those of you coming from the world of traditional photography, when I say aperture, I mean the physical diameter of the telescope, and I don't mean the f number. This is what determines the maximum angular resolution that the telescope can achieve. Angular resolution is the smallest distance between 2 points that can be distinguished by the instrument. It's determined by d, the diameter of the telescope's aperture, as well as lambda, the wavelength of the incoming light. I will not go into detail because the wavelength only becomes relevant at very high resolution photography, typically of planets and the moon. Therefore, disregarding lambda, we can use this formula to compare the resolution of these two telescopes. We can see that it is directly proportional to the diameter only. We cannot make pixels infinitely smaller and expect higher resolution without increasing the aperture. This is one of the reasons why larger telescopes are almost always superior. In addition to collecting more light, as long as the atmospheric conditions allow, they will resolve more and finer details. One of the reasons you don't see professional astronomers with one of these. Conclusion, in my opinion, understanding the relationships between resolution, field of view, and magnification is absolutely key to mastering astrophotography. Understanding these concepts can help you pick out the correct combination of instruments that are more adapt to your preferred targets, or in case you have multiple rigs, it will help you select the best combination for each target every night. I hope that this video has shed some light on some of these very important concepts. If you have any questions or comments, please leave them below. And as always, if you enjoyed this video, don't forget to subscribe so you don't miss more videos like this. That is it for today. Thank you very much for watching and keep looking up and clear skies.